Hey everyone, this is Iain Crosby. This is our video tutorial of our final project for Computer Science Course 177, Intro to Scientific Computing. And our final project is on the partial differential equations package, toolbox, I should say, for MATLAB. And so I'm going to begin our video tutorial with just a brief description of what a PDE actually is. A PDE is a partial differential equation. So to begin, let's just start with a definition of ordinary differential equations. So in mathematics, an ordinary differential equation, or an ODE, is a relation that contains functions of only one independent variable and one or more of their derivatives with respect to that variable. So a simple ordinary differential equation would be f double prime of x is equal to negative f of x. And so the solution to this would be either sine of x or cosine of x, or any linear combination of sine of x or cosine of x. Going on, another important example of an ordinary differential equation would be Newton's second law, F equals ma, and this is a ODE simply because acceleration is the second derivative of the position equation. So this satisfies the conditions of what an ODE is. Now on to PDEs, or partial differential equations. So a partial differential equation is similar to an ODE, except for PDEs deal with multivariable functions, so f of x and y. So it describes two variables. And so an example of a PDE would be the wave equation, which models the motions of waves such as in vibrating strings. So the wave PDE is, let me get it up here for a second, this equation right here that I'm circling right now with the cursor. So what this says is that the function u of, so what this says is that u is a function of t and x, where t is time, x is position, and that the second derivative of u with respect to time is equal to a constant squared times the second derivative of u with respect to x. So this is an example of a PDE. One method of solving the wave equation deals with a technique called separation of variables. However, this is more of a mathematics lecture than a computer science lecture, so moving on. The solution to this PDE, or PDEs in general, are generally highly dependent on the initial conditions as well as the boundary conditions placed on the function itself. So this is essentially what a PDE is. Now going to Taha with examples of how we use PDEs.
Hello, so this is Taha. Great, we know what PDEs are, but what's the point of PDEs? In simpler words, where exactly do we use PDEs? PDEs are used as mathematical models for a wide variety of problems and applications in engineering and the applied sciences. Some of the problems that can be solved and modeled include heat transfer in solids, diffusion, electrostatics of dielectric and conductive media, wave propagation in sound and electromagnetics, transverse motion of membranes, finding the natural modes of vibrations in membranes, and structural mechanics problems. How do I use the PDE toolbox to solve these problems? Using the PDE toolbox involves three main parts. The first part is defining a PDE, the second part is solving the PDE, and the third and most important part is visualizing the results. So let's go to how we actually go around defining a PDE problem. When it comes to defining a problem, we must know the general form of the PDE equation we use to define that problem. And this general form could be something like parabolic, elliptic, hyperbolic, eigenvalue, etc. And we must also know the geometry of the problem that needs to be solved. For simple geometries, the built-in function of the PDE graphical user interface may be sufficient. They can be drawn manually using a mouse. In the GUI include intersections, unions, or differences of basic shapes that include squares, rectangles, ellipses, and even irregularly shaped polygons. For more complex structures, an equation for the geometry of the shape can be entered to the command prompt. Next, boundary conditions need to be specified for the edges of the object and the edges of the subdomains. These come in the form of Dirichlet and Newman boundary conditions. Dirichlet conditions specify the value the solution must take on the boundary of the domain. A Newman boundary condition specifies the value the derivative of solution is to take on the boundary of the domain. Next part is solving the partial differential equation. The PDE toolbox uses the finite element method, or FEM. The FEM involves creating a triangular mesh. Let's take it down to so you can actually see what I'm talking about. Great. So the FEM involves creating a triangular mesh across the geometry of the object and solving each of the vertices of the triangles. FEM is useful because often exact solutions are unattainable and estimations may be sufficient. The triangular mesh must be initialized and refined carefully. If the mesh is initialized but not refined or improved, some areas of the geometry may have less accurate estimations of the solution than desired. If the mesh, on the other hand, is made to be too fine, MATLAB will spend too much time computing, so you need to have a careful balance. Once the triangular mesh is in place, MATLAB will solve the PDE. And finally, the most important part, visualizing the results on a graph. The results of the PDE solution can be visualized in several ways. The default option is to see a color grid with a color bar axis. Other options include the use of contour lines, a 3D plot, and animation mode. Animation mode plots the solution to the equation as a function over several different graphs depending on what time steps were specified in the GUI. Alright, so I'll hand it over to Noah, who can cover for us like a few specific examples regarding how to use this toolbox, and hopefully that'll be a great asset to learning about PDEs and MATLAB. Thank you.
Hey, this is Noah. I'm going to talk about actually using the PDE tool. So for those of you that aren't familiar, what you should do is you start off from the command window. And actually, I should close this right now. So, like I said, we start off from the command window, and what you do is you type in PDE tool. Hit enter, and the GUI will come up. Now, the first thing you might want to do is specify the partial differential equation you'll be working with. One cool feature is application mode. It goes under options, application, or alternatively, on the toolbar, you can just select whichever application you want. While I talk, up here is the main menu, and below it is the toolbar with all the symbols. The toolbar is just for they have a lot of the same options, but the toolbar sometimes has functions that are just something you'll be using more frequently, so it's for ease of use. Like I said, we specify that we're using a heat transfer. To specify exactly the PDE, we go to the PDE option and PDE specification. Now, this is a parabolic equation. The application mode changes the abstract symbols from the same partial differential equation into the equivalent of the parameters that we'll be dealing with. So this is more of an engineering question, exactly what these numbers will be for a certain material. For us, we're just keeping it simple, just showing how to use the program. In the write-up, we specified that Q would be 2. So I'm going to make it 2 here. And we can specify the geometry, as Taha said would be the first step. Now, over here in the toolbar, we see some objects. We have an ellipse, and we have rectangles and circles. The plus just designates exactly where the object is drawn. So for example, if we click on the rectangle, we see that it draws from an edge. Now let's delete this and let's click over here, and now we see that it's drawn from the center. Now if we double click on an object, it'll bring up the object dialog box. We specified that for this rectangle, its center was going to be at 0, 0. Its width was going to be 4, and its height was going to be 2. Now as you can see, this is now out of the bounds of our axes and we can't visualize it well. So we go to the options menu and let's go to the axes limits. Now let's make the X range auto and let's change the Y range from 0 to 5. Now we see we get this. Now let's change the axes to equal each other, and now we get exactly what we might actually be looking at with these dimensions. So our next step would be to specify the boundary conditions. We can go to boundary mode, or alternatively we can click on this little symbol partial omega, where omega specifies, well, where partial omega just specifies the edge. So if we hit it, the object changes and we have these arrows that represents the edges. So double clicking brings up the boundary conditions. As we can see, I specified earlier that the top and right boundary would be Dirichlet conditions, and as we can see,
This is exactly what we want it to be, as specified in the write-up. And this appears to be the same as well. Now, for the bottom, it's a Newman condition. So we select condition type, Newman, and G is equal to X. In our case, Q is equal to 0. And for the left boundary condition, we double click. It's Newman again. Now, G is going to be 1, Q is still going to be 0. We notice that the colors change for these edges. Blue is blue is a Newman condition, and red is a Dirichlet condition. This is just for visualization. And next, we want to go to solve parameters. Just because we're going to be using the animation mode in a second, we want to specify the time that we're solving this for. Linspace is a pretty good command. And our arguments, 0, 5, 10, this just specifies a vector where the lower end is 0, the upper end is 5, and there are 10 elements. So each of these elements might be half of a unit. So at our initial time, we specified that temperature will be 0. The relative tolerance and absolute tolerance are actually something that has to do with the finite element method in calculating the numerical solution to our PDE. And it's out of the scope of what we're dealing with, but these values do work for us, so we're not going to have any problems. Now, the next step would be to initialize the mesh. We can go to the mesh option in the main menu, initialize mesh there, or we can press this little triangle over here. And we see we get a bunch of triangles, and we could solve it right now. And it does work for our purposes, but just for the benefit of the viewer, I'm going to show about refining the mesh. So the first step is we click these little 3 triangles over here, or we could go to mesh and refine mesh. First thing we should do is we should jiggle the mesh. Again, this has to do with the finite element method. We see that this did change a little bit, and it has to do about seeing if deviations from what the refinement was create less overall error. If we choose jiggle mesh again, we see that it doesn't change all that much. So let's say we want to stick with this, and we decide that this will give us enough accuracy. We can always go back if it doesn't. The next step would be to actually solve our equation, and we can do that by clicking this little equals button, or we can go under the solve under the main menu and click solve PDE. As we can see, alright, this is solved, and the default is a color bar. It's solved at the last time step because I did earlier specify that this would be solved over different time steps. So this is very self-explanatory. We see that, well, exactly what we would expect to see. So our next step would be if we want to plot this in a different way. So let's go to the plot and parameters menu. We can choose different plot types. For example, let's say we want to plot height in 3D and contour. We can do that just by specifying these over here. We click the plot button, and we're going to get a figure that pops up that we can rotate, and we just have another way of viewing our solution. Now, regarding the animation mode, all we have to do is, since we've selected different time steps, we hit animation. I'm going to take off contour, and we're going to plot it. We're going to have a figure that comes up, and as we can see, this actually does evolve a little bit over time. Temperature does equalize pretty quickly, so we don't see all that much change. But that's just for the benefit of the viewer. So that concludes working with this partial differential equation. Or actually, I'll go over one more thing before I conclude this video. We can save these. So let's say we're going to save this. I'm going to save it as a file called test. So what we can do is we save it. As we can see, this has already been solved. I'm going to close this box. Over here, I'm going to open up test.m. We see we get a script file. Now, if we run this script file, as you can see, PDE tool pops up and it plots, well, it just goes to the last step that we performed when we solved this. In this case, was the animation mode. So, thank you for listening, and I hope you got something out of this. So, if you want any more detailed information, just look at the write-up. It contains a lot more information, and hopefully this should answer any other questions you might have about the PDE Toolbox.